Hello, we are group number 9 and in this video we will explain the design and simulation of an impeller using computational fluid dynamics and the comparison of this impeller with one that is commonly used in the industry, better known as the Rushton impeller. The agenda for this presentation is: first, we will explain the importance of the characterization of an impeller as well as common variables used to measure an impeller's performance. Then, the methodology implemented for both the Rushton and the impeller design will be explained along with certain parameters worth to remark. Later, results from the simulations made to both impellers will be displayed with the residual curves, the power number curve, and the animation of the simulations. After, a proper analysis of the results obtained will be made, highlighting the improvements achieved with the new impeller. And last, conclusions from this project will be made in order to characterize properly the study case and suggest which impeller performs better. Mixing and agitation are two of the most important operations of liquids in many types of industries such as pharmaceutics, food, and more recently biotechnology. The main objective of the mixing process is to provide a mass transfer by means of a better contact between the different substances in such a way that the required product is obtained in the shortest possible time. The final product is determined through the type of impeller and the characteristics of the tanks, such as the presence of baffles, variables which directly affect the generated flow. The most common types of impellers are the turbines, the anchor agitators, and the simple propellers. In the bioprocess industry, the commonly used impeller is the Rushton type, which imparts a radial flow. A great disadvantage of this type of impeller is that it does not generate a uniform mixture throughout the stirred tank, with a large shear near the tips of the plates but much less towards the periphery of the bioreactor. In order to measure the effectiveness of an impeller, indicators such as power and shear rate are commonly used. Power is widely used because of its costs implications. It is calculated from the torque applied and the equations can be seen on the screen. The shear rate is also important because it provides a great fluid intermixing and homogenization. Also, values such as Reynolds number and the power number are very important in the system because they explain the regime of the flow inside the tank and because they can be standardized units of measure applicable to other systems. It is important to mention that during the last years it has been used a computational tool, computational fluid dynamics, that allows to model the behavior of agitated tanks through different geometries as well as different types of impellers. These simulations allow obtaining profiles associated with velocity, shear stress, among others, thus characterizing the efficiency in terms of a required process. For this project, two impellers were simulated, a Rushton one and one designed by the members of the group. The Rushton one is composed of 6 flat plates and has a diameter of 0.051 meters, and the one designed is composed by 8 curved blades with the same diameter. Also, both are simulated in a tank with the specification proposed in the guide and with 4 baffles. Regarding the mesh, the type of cells used was a polyhedral one because it makes a better fit in both geometries and because it can guarantee certain degree of homogenization between cells. The cells generated for the Rushton impeller were 484,968 and 524,829 for the design one. Both values are close to 500,000, which was the main objective. The rest of the parameters regarding the mesh were given in the guide, which were a prism layer thickness of 1 mm, 72 points per circle of surface curvature, and 3 prism layers. In the model specification, it was assumed a pressure of 0.64 atmospheres because of the atmospheric pressure in Bogota, and it was described to be water the fluid to be simulated. The K-omega model was chosen because it can work with laminar, transient, and turbulent regimes, and gives an approximation of Navier-Stokes equations through the differential equations shown on the screen. After completing all simulations for both impellers, the residual plots could be obtained and the values regarding certain variables could be gathered. Simulations for 5 different Reynolds within 3 different regimes were made. For Rushton impeller, the results table is here shown, which shows the power number obtained from the simulation as well as the ones obtained from literature. Also, values such as Reynolds and the angular speed are shown. Then we can see the cell quality, skewness angle, and the wall J+, where can be seen that the mesh has a good quality. In the animation, the movement of the fluid happens near the impeller, but becomes smaller as it gets away from it. This animation was made by taking a series of photos and after putting them together and increasing the speed. The residual curves show oscillations between the simulations, which are made in a non-steady state, but they tend to stabilize as the Reynolds increases. For the impeller design, a table of results was also generated which shows the same values than the raster one. The cell quality, skewness angle, and the wall J plus also show that the mesh generated was accurate. And here, in this animation, the fluid begins to move through the entire tank as the impeller begins to rotate, and also shows a better degree of mixture in comparison to the Russian impeller. The residuals curve also shows certain oscillations due to the non-steady state as mentioned before, but also tend to stabilize when the Reynolds number increases. The power number curve gathers the information of the theoretical values for the Russian impeller, the simulated values for the Russian impeller, and the simulated values for the design impeller. Here it can be seen that the tendency of the curves is similar and the simulated Russian is close to the theoretical one. Several analyses can be made from the results obtained before. First of all, when the Reynolds number increases, take E increases due to the regime generated for each Reynolds number. Due to the oscillations in the residuals, the results in the Russian impeller are more accurate compared to the impeller designed. When the Reynolds number increased, the power required decreased, so for a turbulent flow, the Russian turbine needed less power than for a laminar flow. For the Russian impeller, both the theoretical and the simulated data show that the tendency of the power number is the same. Nonetheless, the stabilization of the power number curve was granted in the transition regime for the theoretical values and in the turbulent regime for the simulation. The shear stress increases as the regime changes, Reynolds increases. A sudden change in the increase rate is presented when the regime changes due to the irregularity in the movement of the fluid. About the power number, the design impeller is not the accurate option to work with laminar flows because of big values of the power required. However, for turbulent flows, the power required is similar to the power required for the Russian impeller. The mesh quality is lower for the design impeller due to its geometry, angled blades. However, its mesh is still acceptable for the standards imposed. About the results in comparison with the literature available, it confirms that one of the disadvantages of the Russian impeller is the non-uniformity because the shear stress is greater near the blades. In relation to the type of fluids, Newtonian or non-Newtonian, for the last one it's impossible to assure that it's more difficult to represent appropriately the behavior of this one because the relations between the variables changed and it is necessary to make different assumptions than for the Newtonian fluids. To conclude, the impeller design has a bigger shear stress than the Russian impeller, thus completing the objective of the project. Nonetheless, the design impeller requires a greater quantity of power for laminar regime, so it is better to work with it in turbulent regime. For a turbulent flow, the impeller requires less power because of the energy available in the type of flow. The J plus indicates that the quality of the mesh for the design impeller is accurate. However, it is less precise than the mesh of the Russian turbine because of the curved blades. The K-omega turbulence model used for the simulations is appropriate because it represents the turbulent properties of the flow through the turbulating kinetic energy and the specific dissipation. For non-Newtonian fluids, it is required a more exhaustive analysis about the relations between the variables such as the shear stress and the rotation velocity. CFD is an excellent tool that allows to analyze and predict the behavior of many equipment and operations that are commonly used in the industry and can be used with the main purpose of optimize the process. The design impeller has a higher shear stress than the Russian impeller but with the same behavior. It increases linearly as the flow becomes turbulent.